or a second common method to make ethers using SN2 chemistry. Okay, which is a second very common method, the Williamson ether synthesis that we just spent a lot of time on. That's the most important one. Okay, there's a way to make ethers. If we take ethanol and add a very small amount, or a catalytic, or a dilute amount of strong acid, there's a way to take ethanol and make ethers from it. If we look at this reaction really carefully, if we were going to balance the thing, we definitely need 2 of these. Otherwise, this is impossible. And if we really wanted to balance it, there'd be a molecule of water coming out the back end of this too. But that part really isn't so important for us. But there's a way using SN2 chemistry to make ethers. If we just take ethanol and another molecule of ethanol, it's very unlikely that these are going to undergo an SN2 reaction. It's very, very unlikely for 2 reasons. One of these molecules would be the nucleophile, the other would be the substrate. So let's think about this attacking and this leaving. This won't happen for 2 reasons now. We've seen the bad leaving group trick already. I can't pull that one on you twice in one day. This is a bad leaving group. And this is a very poor nucleophile. Substrate's fine, it's primary, but this isn't going to react very well. It's electronegative, it's also neutral. Just would not be a very, very good nucleophile. This would be a horrible leaving group. This will never work this way. But let's try this acid trick again. Let's do an acid-base reaction, and the nature of this acid is really not so important. If we take a tiny, tiny amount of this stuff, it can undergo an acid-base reaction. We make a tiny amount of this with a ton of unreacted ethanol present at the same time. We know at least that we've converted a bad leaving group to a good leaving group. If this leaves now, it leaves as water, which is a very, very weak base. So let's try this SN2 reaction again. Again, this isn't a good nucleophile still, but now we have such a powerful leaving group that this can leave. And what we're left with here is water. And we'll carefully draw the result of this. A little bit out of space here. I might have to restart this. Maybe not. Okay, so this is what we would get from this SN2 reaction. It's an oxonium ion. It's highly acidic. This proton could be plucked off from water, could be plucked off from the conjugate base we're dealing with. We have lots of ethanol. It could be plucked off from lots of places. That's not really the point of our discussion here, but if we do an acid-base reaction and remove this proton, we get back to our ether compound. In this particular acid-base adjustment step, we actually regenerate an acidic proton. So this could get picked off from water, and we get hydronium ion. We have a little bit more of this strong acid. This reaction can happen over and over and over again. So we can make symmetric ethers, starting from alcohols and a small amount of strong acid. It's a little bit convoluted here, maybe the most difficult thing to study. Make sure you study and understand the Williamson ether synthesis first, master that, then spend a little bit of time on this. But I'm really not trying to overwhelm you with lots and lots of different things today. But this is important. You should study it, but not at the expense of Williamson ether synthesis, which we studied moments ago. Okay, so practice this, go through it, work it through, and you'll understand and see how this works, how it's an SN2 reaction, and that's a modification of making a bad leaving group a good leaving group. It's also where the same molecule can ultimately play a role of substrate and nucleophile. And this reaction actually works. If you take ethanol and waste a perfectly good bottle of ethanol, you can make diethyl ether. If you want to make diethyl ether, I don't know what you young people want to do with yourselves, but you can mix a little bit of acid, a bottle of ethanol, heat it, get diethyl ether. So those wrap up some important things we've worked on today about SN2 versatility, about converting bad leaving groups to good leaving groups, some applications with making ethers now. The first most important method was the Williamson ether synthesis. Second most important method, we could take alcohols and add strong acid. We're going to now talk about one or two last things with our time together today. We're going to talk about amines as nucleophiles. At the end of our last lecture, we did 4 or 5 back-to-back rapid examples of SN2 reactions with a whole variety of powerful nucleophiles. But amines are kind of intermediate nucleophiles. And there's some funny problem with amines that we're going to describe today. And I want us to explore this idea of changing reactivity as a reaction takes place. Let's take a simple molecule, ethyl bromide, and we're going to take ammonia as our nucleophile. Okay, so right now we have enough information to try an SN2 reaction. Nothing funny about this at all. You can at least try it, see what we get. If we do this, see what happens. We get nitrogen in place of bromine. Bromide's a great leaving group. Substrate's primary, it's perfect. Nitrogen, well, it's hard to say if it's a good nucleophile, but if we look at it in the periodic table, it's less electronegative than oxygen. And amines and nitrogen, with a pair of electrons, actually can be nucleophiles, even if they're neutral. We could make this a better nucleophile if we pulled off a proton and made it the negative form, or its conjugate base form, but as written, this will react. This particular species here is known as an ammonium ion. And just like an oxonium ion, it's acidic. It can undergo an acid-base reaction. We have lots of things we could do an acid-base reaction with this particular mix of things. It turns out that ammonia itself is actually basic. So we do these reactions, and we know there's millions of these molecules we pour in, so there's always lots of ammonia floating around here. And this can undergo an acid-base reaction, and we end up with a primary amine as our product of this SN2 reaction. Okay, there's one little acid-base step in between the beginning and the end. Don't get too worked up about it. Practice all the other SN2 reactions. Then when you get to amines, you just see this non-neutral product here, and it should be a reminder, we have a plus charge on either oxygen or nitrogen and some hydrogens. These are acidic. We're just going to remove them, and we're going to make a neutral compound. Right? If this was O with 2 H's attached to it, we'd take off 1, and an acid-base reaction would make alcohols here. Okay. This particular reaction is a little bit funny, because please always remember that there are millions of these molecules. Million isn't even appropriate, right? When we do a reaction and we put a milliliter of something in there, it's not like million. It's like billions of molecules, right? So huge, huge numbers here of molecules when we start this reaction. On paper, we're writing 1 and 1, but if we do this reaction in the real world, there's literally like moles of these things. 1 times 10 to the 23, or if we're doing millimoles, 1 times 10 to the 20 molecules. So billions of molecules. So this reaction actually has an unintended consequence. We start the reaction, and it does make this primary amine. So it goes here, makes ammonium ion, molecule of ammonia plucks off this proton, and we get a primary amine. This primary amine compared to this amine, right? So this primary amine compared to ammonia These are now both present in the reaction. This is almost like that consecutive reaction we saw with radical reactions. These are both present now. But this particular compound just became more basic and more nucleophilic as compared to ammonia. And it does so because we have this carbon group attached to it now. And we saw this effect with acids and conjugate base stability. This would add a little bit of electron density to nitrogen. So between these two species, this one actually becomes a little bit more nucleophilic. If we were comparing these in terms of their acid and base reactivities with HCl, this one's a little bit more reactive. Okay? And it's due to this electron donation effect. So this reaction goes once, and the point about amines as nucleophiles, they're problematic. Let's add that now because we're going to go to the next page, but when you come back to your notes, I want you to know that these are problematic. There's a problem here, and that problem we're going to uncover together here. Amines are a little problematic to me right now because I don't have a stack of paper within arm's reach, and I have long arms. So sit tight for 1 second. But I want you to think now about this, that this reaction's going on, happens one time, and we have hundreds of thousands and millions of these molecules, and we just made one of these, and they're all sitting in the pot together. So we actually have two nucleophiles in the same reaction in one substrate. That's where we're going. And I'm just going to bring back a huge fat stack of paper.